Question 4, air cargo. A plane follows a specific path. At each stop, we call ports labeled with numbers. Cargo can be unloaded from the plane and then loaded onto another plane. All the ports are equally distant and all planes travel at the same speed. That simply means if this was a graph, it would be undirected and unweighted, and everything's connected to everything by the planes, which is not too much of an important fact unless, it's not important in here. Just make sure that, anyway, in a system, it's just a fancy word, there are multiple planes which all follow the same timing schedule, meaning they all leave their respective ports at the same time. So all that this is saying is a plane would start at time equals 0 at 1, and then time equals 1 at 2, 3 and 4, and then go 1, 2, 3, 4, and all the while it would go, the other plane would go 4, 2, 4, 2, 4, 2, and a postman's job is to get cargo from port 1 to an end port as quickly as possible. The thing with this Olympiad is that it tries to give these italic names that it barely references afterwards, and then simulate the job of a postman, and it likes using in the form FF something, so that's just something to be mindful of if you're doing this type of Olympiad for the first time. Then what we want to do is get something from port 1 to a destination port as quickly as possible, which means be on the plane for as short as possible, which means minimizing T. So all we're doing at each step is being on the plane. You have the option to switch plane or not switch, but essentially you're just choosing which plane to go on to. So at port 1 times 0, you only have this one plane, but then you follow this plane to port 2, then you have another option, that is going on this second plane. And then on the next time interval, unit, whatever, you'll be in port 4. So that is the quickest way. And when you see distance of the shortest path, things like that, you should automatically think it's just like the BIO if you're doing it. Question 3 is mostly just BFS, DFS, DP. And in this case, we are simply searching if we choose to be on this plane, how long it would take. If we choose and go on this plane, how long it would take. But since we're looking for the minimum time, it means the minimum steps taken to go to the next time frame. So we're going to use BFS, if that's clear. What we're first going to do, here's my code. It's a very lovely extension. Lets you put in all the test cases. That's on the mark scheme. And the reason I'm doing this video is that the mark scheme doesn't really tell you anything because it's a spec paper. So this is my working. If time is 0, then everyone's at its first path port, first port in the path, and then time equals 2 in the second one, 3, then this would loop back. So the index for stop is T mod length of path, which just means if your path length is 2, then you want the third one, then you're going to be at, so time equals 1, you're here, 0, you're here, 1, you're here, 3, you're here, which is actually here, which is 3 mod 2, 3 divided by 2, and take the remainder, which is 1. And then if you're 4, then 4 divided by 2 gets you 0. Yeah, but our index is 3, and we're 0 index, so it's go back to 1. Don't worry if you don't understand this. And what we're going to do now is first take the input. We take the input, and then we're going to set up our BFS, which we need a queue for. I just use this one because it has this pop left function. This is in Python, but should be pretty much the same in any other language. you have to import it from collections. That's your Q. You pop it and stuff. And basically what you're doing is you store the ports that you're at and the time you're at it. Because if you were at 1 at time 0 versus at 1 at time maybe 20, it might be different which path of planes are available to you in case the paths are really long and convoluted. And then we add this to the queue, just put it to the back. And while not empty, we take our port in time. And if we're at the end port, we can just break. That's kind of our base case here for plane and path. So you have all these planes. Here's your end port. Here's the number of planes you have and the path of the planes. And then you're going to check where every plane is at this point. So this is my index. This is the length of the path. This current time. So you index and get wherever this plane is at. And if it's at our current port where our cargo is, then we can try to search that. We can explore the option of switching to that plane and go into its next destination, which is given by this bit here. So in the next unit of time, replace t with t plus 1. And one thing to be mindful of, a mistake I've made is I didn't add the brackets, so kept getting out of range error because you got t plus 1 mod length of plane instead of t plus 1 mod length of plane. You add your new state to your queue. I like to call it frontier because that's how I learned it, but it doesn't matter. Then it will just keep going. It will explore these options until you find it. And because you're using a queue, it's BFS. Another mistake I've made is I did pop instead of pop left, so it was actually using it as a stack. Yeah. Turn to DFS. And this is deceivingly complex. I can show you the code that I wrote 2 years ago when I first saw this. It's deceivingly simple, perhaps. I tried to do a bunch of edges. And then let's look at the code in its full glory. It was just way too many lines. Tried to make an edge and explore the edges. I had the same queue thing. This is basically the same. I don't understand what this was going on. I think I was trying to implement... I don't even know. Did it work though? I was definitely overcomplicating it. Okay. Just take one test case and try to run it on here. I don't even know if it's finished. Yeah, fantastic. But we don't need this much of stuff, okay? Just so you know. Just keep searching. Boom. Done. And then I wrote a little test case generator function for the plane, the number of planes, and the length of the paths, just because. Then E is my endport. I took a random endport, but the endport is also the number of ports I put. So, it's basically generate a random length of paths, and for each length, for each bit of path that I have to fill in for this particular plane, I would get a random number and just some space. If it's not the last one of the row, then don't print a behind it. Print a new line after everything. Okay, so we could put in the simple test case. Well, these are all my randomly generated test case anyway. If we put it in a debugger, you might be able to see this work. So, int input paths, then just map and pistol it for how many times. This kind of basic Olympiad style question input taking way. And then you have your queue. You're initially at time equals 0 and port equals 1. And then, boom, we have a port in our time. It's not our end port. Our end port is 5. Then for this current plane, it's this path. And then we take the path. Yes, we're at there. So we add state 2, 1, which means we've taken this plane to its next destination, which is 2, and then 1 unit of time has passed. And this just keeps happening for every plane. I sort of skipped over the good bit, but at some point it would pop a node that has the end port, and the T would be minimal because we're exploring. It's BFS. Yeah, it's BFS. Now, part 2, part B, the permute function just gives you the definition. Basically, takes R is the length of this subset you want, and N is the total number of stuff in the superset on the big set. S, and then you can do A, B, B, A, C, A, A, C, all these combinations in any order. And it introduces the complete system, which every port is connected to every other port. Find an expression in the form sum of fn with the number of paths between two ports, P1 and P2, and it consists of complete systems, so no ports business more than once. So it doesn't want you to go, if you want to go from A to B, it wouldn't let you go A, B, A, B. That's the no port visited more than once bit. Then if you wanted to go from A to B, then you have 4 ports, and they're all connected to one another. Right. What is... So you could go from... Here's 1 and 2. You could go directly, or you can have the reverse, or you can go here to here to here. No, I mean here to here to here, here to here to here. But essentially, you're going like that, there is only one unique path to do this. And then another way to do this could be here to here to here to here. So if you're going 1, 2, or you can go 1, 3, 2, 1, 4, 2, or 1, 3, 4, 2, 1, 4, 3, 2. And then you can do the reverses of that. Actually, from here you can see that the middle elements can be switched in any way you like because they're connected to each other anyway. And what we're essentially doing is you have to set 1, 2, 3, 4. You want something with 1 at the end, 2 at the other end. And they didn't give you the permute function for nothing, right? So you can apply that here. So you can have, initially you might think, 4 elements make something of a length 2, but then you also get things like 2 to 3 and 3 to 4. So there's something you're actually not allowed to be choosing, which are the endports. So instead of choosing the whole sequence, we're trying to choose what's in between them, the path, the interim nodes. So you actually have a set of n-2, and you can permute in any order, whatever this middle thing is. So in the middle thing you have 0 here, 1 here, 2 here. So in the mark scheme they've called it K, and then you just search through every length of interim nodes you can have. So that's from K equals 0 to, you can include all of them, and all the interim nodes, it's just n-2 because you're excluding the endports. Let me just move this out. So that's essentially the solution. Yeah, I had to really look at the solution in order to really figure out how they wanted me to use the formula. But yeah, there's the explanation. And for the third one, I think it's just quite simple algebra for a bit, as you can see in the mark scheme. So you want the sum of f of n, and you can basically just expand out the answer to b, and that is what it is when you do that, because they've given you the formula as well. You just sub things in for a bit and you get a few marks. Then this is kind of funky. This bit I don't quite understand, so it would be great if anyone could explain it to me. But even if you can't, you just write down a bunch of working, you'll get a couple of marks. It's better than a bunch of people scored 0 or 1. So if I were to actually try to take this forward, let's see what I would do. You have your n minus 2 factorial, or there's obviously 1. Because this is what it's given us, n minus r, and we started seeing at n minus 2, there, so n minus 2 choose 0, n minus 2 minus 0 is still n minus 2, so that's the bottom bit here, n minus 2 factorial, because this bit actually never changes. Then you minus 1, because k is 1, we minus the r here. Okay. Just one more. 4, sorry. Dot, dot, dot. Then you can factor out the n minus 2. And you're left with the 1 over n minus 2 factorial plus something n minus 3 factorial. Yada yada. Then you'll have to factor e into this equation, because sometimes it's best if you could provide an end point to your factorials, because eventually you're going to n minus 2 minus 3, and you get n minus n minus n minus 1, and then 1 over n minus n, if you keep going like that. Actually not. It's not n, is it? You're having k to eventually be n minus 2. So there's n minus 2 minus n minus 2, just for the sake of correctness. Factorial. Factorial, yes. Because at the very end you'll have n minus 2 choose, permute n minus 2. And that is the same as saying we have n minus 2 things. You want ways to select n minus 2 of them and include all the different orders. So it's basically how many ways you can order n minus 2 things. Wait. So it's basically just n minus 2 factorial, yes. And 0, this goes into 1 over 0 factorial, which is 1 over 1 by definition. That's 1. So you'd actually have n minus 2 factorial, and then all the same stuff there, and then you have 1. And the thing before is 1 over n minus 2 minus n minus 1. Hold on. Something might be wrong. I expect 1 to be down here, honestly. Right? No. N minus 2 minus n plus 1 is equal to minus 1. I don't know how you could get minus 1 factorial. It's weird. Yeah, because of course it's not n minus 1. N minus 1 is too big. It's bigger than that. It's actually n minus 3. N minus 2. Okay, that's increasing. That makes more sense now. Take away the n, you just have 1 factorial. Is it 1? Kind of. Okay, so the next one, you'll have on the bottom bit 1 of 2 factorial, and so on. You get. Sometimes you need to, with these infinite, very long series of things, you better convince yourself that it is the case, whatever you're saying. Okay, maybe. Now, something looks familiar. You look at the equation for E. You still have your 1 over n minus 2 factorial and stuff, but then here's 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial, all the way up to n minus 2 factorial. That's how it is. So this bit, because E is this infinite bit, E is this bit plus all the numbers that, all the natural 1 over natural numbers that comes after 1 over n minus 2 factorial. You could try to make something out of it. So you got E times n minus 2 factorial. So you'd want E in this back bracket anyway. Look at your little goal. Somehow. And that is E minus all the numbers, all the 1 over. Well, don't forget the plus 1 first of all. And this bit is 1 plus blah 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 up to something, some massive number like 1999 factorial, and then you get 1 over n minus 1 factorial, 1 over n factorial. Okay, so because E is this infinite series, that, so you have E, which is this 1 over thing, 1 over thing, 1 over n, something, 1 over 1 factorials, and then what we have is 1 over n minus 2 factorial here. So this bit is equal to E minus everything that comes like after there. So we'd include that bit, the n minus 1 bit. Let's move this to the side. Now, what is this number actually? You know that this series is going to get really ridiculous because you're going to have 1 over the factorial of this massive number, which is equal to 1 over massive number times massive number, which tends towards 0. Right. Okay. So I don't know how many terms would make it less or more significant, whatever, but what we have here, we have kind of what they want. We've got the E multiplied by n minus 2. That's E n minus 2 factorial minus this massive thing. plus, I don't know if I'm doing this correctly though. So you got this bit. Yeah, n plus 3 and so on. Okay, so it's done this, let R equals for this infinite sequence. So let's follow that. Then, hold on. For some reason they've missed out this other one that I've been looking at. Have I made a mistake? N minus 2 factorial over 1 factorial. Huh? So when they have n minus 2 factorial over 1 factorial, that's came from n minus 2 permute n minus r equals 1, so n equals r plus 1. What? N is equal to n minus 2 plus 1? That makes no sense, because I thought it's supposed to be inclusive. I don't know, is there a mistake in this? Might ask someone later, or if you know why, do tell. Okay, apologies. Just realised how messy my working looks. So maybe we can put that aside for now. So, it's kind of the thing where you have geometric and arithmetic series combined, when you multiply by 1 over r, but r's getting larger by each term. Things like that. I'm not going to go into because, yeah. Okay, but of course it's going to be less than 1, because I don't know how to precisely show this, but because this is going to be less than 1, that's less than 1. You're going to have this long tail of, so 1 over the factorial of stuff, even if it's just the graph of 1 over x on the positive side. Anyway, we'll take it for granted. See what's it doing. So we want the floor of this value. What does that mean? Okay, it's because this is going to be some massive value, and then minus this small decimal. We want to show that this whole expression is equal to floor of that value. So in some way, this is going to be something dot something, like a decimal, like 52.589 or something. And if this is equal to the floor of that, that means this bit must be equal to 0.589. If you minus that, you get just 52. It means flooring it, chopping off the decimal. I don't know how to get past this show that 1 greater than r thing. But then you have this r expression as basically just what we've been writing, and you expanded that out. I really don't get how you just jump from this to that. Well, let's see if this is true. N minus 1 times n smaller than n minus 1 squared? So minus 1 squared is 2n. That's weird. Okay. Why is it less than? Just who did this? Okay, even when we say that's true, then how did this come? Just why? And then it's all of a sudden just 1 over n minus 2 is smaller than 1. Honestly, just do what you can. Okay. Well, there's question 4. I don't know, I might do the other ones, but I know it's pretty late. We only have like 2 days until the actual thing. So if you're watching this, good luck. And just practice coding it. Practice doing the questions actually, instead of thinking, okay, I understand this, but you might actually struggle some maybe mistakes, careless mistakes that you always make, but you need to sort this out. So yeah, bye.